This meeting is being recorded.
Okay, and now our official start of class. Welcome everybody to data mining today. We have a couple quick administrative things before getting into the fun technical stuff. First of all, over here on the GitHub issues, as a reminder, all of the announcements, everything in this class, I will be posting in issue. And again, all of the lectures here will be recorded and put on YouTube. And if you click this link right here, you'll be able to go find those videos. I will not be posting like announcements every video I upload, but just a couple hours after class, there'll be a new video there that you can go to and watch. If for whatever reason you are not able to come to class, you can just watch those videos. Or if during class you miss something and want to catch up on it, you can see those videos. A couple of people, let's see if I go back to the main page. Actually, if I just click this button to do it faster, under this this watch button right here, it shows there's 49 people watching this repository. Like 30 of those are from past semesters that people have not unwatched it yet for this repository. So they're getting a whole bunch of email announcements right now, which they probably don't want. But if you want email announcements for this class, which you probably do, then you should click this watch button right here if you haven't done so yet, so that anytime I do make an announcement, you will get notified of that. Last thing related to the GitHub stuff is that if ever you do find a typo on the web pages, again, if you submit a pull request to fix those typos, you will get extra credit. And one person has already done that and gotten 1 point of extra credit here in Sakai, Ambika. So currently has a infinite % in the class. It's 1 out of 0. But if you would like more, like to help me, I'm a puny human. I have a wet, squishy brain that makes mistakes all the time. And if you see one of those mistakes, please come and fix it for me. Help me out. Okay. Any questions on anything administrative? Did I see your hand? Okay. Yes.
How are the extra credits counted?
The question is, how are the extra credits counted? And in this case, if you do fix a typo somewhere, it'll be worth 1 point for the first one, and subsequent ones will be worth less points, but you'll get even more respect from me, which is even more valuable than points in the class. But all points in this class are treated equally. So on the categories down here, you can see that the final, for example, is worth 2 to the 7 points, which you should all have memorized as 128. Our exponents of 2, super important in computer science. So all of our class projects and graded things will be out of powers of 2 to get you intimately familiar with all of these numbers here. So yeah, no point is worth more than another. There's not like percents and categories. It's a point's just a point. So that 1 point on the extra credit, not probably going to make the difference directly in your grade. There's probably going to be 200 to 300 points overall. But again, all of our evaluations and things in this class, the majority of your points are going to come from oral exams, one-on-one with me in the office. And so the more of those, I don't know, soft respect-ish points that you've gotten, even if it's not directly included in your grade, might make the oral exams at least feel easier for you. A good question. Any other questions about anything administrative in the class? Okay. Last time, so we started doing some technical stuff here in our topic 0, computation linear algebra folder. And again, the notes.pdf file right here is the file that we have been going over. And you are welcome to take notes either electronically by downloading this file and taking notes inside of that file, or on the printed papers that I passed out last time. It doesn't matter. There will be times in this class on quizzes where you will have, say, open note quizzes, and if it is an open note quiz, you'll be allowed to use your laptop or whatever tablet device you would like to reference your notes, or whatever printed material you would like, you'll be allowed to bring those in. So whatever is most convenient for you is how you should take notes. Here I have a question. Yes. Question is, will I always be printing the notes? And the answer is yes. In like sometime next week, after we've settled down a little bit more, I will take a survey about who likes printed notes and who likes not printed notes. So that all the people who want printed stuff will always have printed stuff that I will bring as it's time to do that. And then the people who are not going to use the printed stuff, I just won't print things out for you, so we're not wasting trees. But people who want printed stuff will always have it available, and you don't have to worry about printing things on your own. Good question. Slight minor inconvenience maybe for those of you who like printed stuff is that occasionally I do find small typos in the notes and will update the PDF file itself. And I did do that since the last time we've met. And so the original version, the printed version that I passed out is this notes-2024-08-26.pdf. And this new version right here, notes.pdf, is slightly updated with just 1 or 2 typos fixed. I'll highlight those typos as we go through the file today. But just for your awareness that if you're just downloading something right now, this is the one to download, has minor typo fixes. If you have already downloaded it or using the printed version, it's still okay to use this. I'll highlight where those typos are as we get to them. Okay, so let's switch my screen now over to the actual notes. This section 3 is where we got to last time. The top of the notes looks like this with the computational linear algebra. And as a reminder, we spent most of our time talking last time about this big O, theta, omega notation. And I have this big, scary definition right here about what the technical definitions are for these terms. Hopefully you have seen these terms a little bit in past classes. But maybe if you haven't, you might not have seen the full technical definition of these terms before. Here's the technical definition. I'm not going to ever ask you to memorize this particular definition. And instead, the important thing is that you will be able to apply that definition in order to solve these problems where I'm asking you, given 2 functions, relate them with the O, omega, and theta notation. And last time we worked a couple of these problems here, and problem 1 and problem 2, and then coming down here to this problem 3. Again, I also left many of these problems incomplete. We didn't do them all in class. Some of them are left for you to work on your own. That we will have a quiz next Wednesday, a week from today. Next Monday, we'll talk about the detailed format of that quiz. But the quiz next Wednesday will come from this notes packet and have problems like these big O sort of problems right here, deciding whether 2 functions are related to each other. This quiz will be an open note quiz a week from today. So whatever notes you're taking in your packets here, you'll have access to them. And again, you can use your computer, access things like Wolfram Alpha during the quiz if you would like to. There will be no restrictions about what you're allowed to do other than don't talk to the person next to you. Let's do a quick problem here. I'll stop for questions in a second, but let's do a quick problem before I do that. Last time, I think, on this simplification here, we did number 1 and number 2. And again, one of the highlights here is that if you have only one variable in your big O notation, that can always be simplified down to just a single term. But if you have 2 variables in your big O notation, sometimes that can be simplified into a single term, sometimes it cannot be, and you might have multiple terms and it cannot be simplified further. Let's go here. I want to do this problem 4 here because this is probably very different than anything you've seen in previous classes, even if you've done a lot of big O notation stuff. And in problem 4, the thing that's different here is that not only do we have, or not every term is an ordinary polynomial where the exponent is a positive number. Now we have these fractions in our big O notation. And for runtimes, this basically never happens. You never have a runtime that, say, gets faster as the size of the data increases. That's this number over here, 1 over n. As n gets larger, that number gets smaller. So if this were representing a runtime, then that would mean the runtime is getting faster as the problem gets larger. That basically never happens. And so that's why an expression like this may be new to you. We will, however, see a lot of situations where we are using big O notation or omega or theta notation to talk about the accuracy of problems in this class. And this is a situation where you do encounter these fractions a lot. So I think in the rest of this note packet, we're going to be talking about some runtimes of things like matrix multiplication. And then the next set of lectures, we'll be starting to talk about PageRank, where we will see our first examples of real world applications, big O notation with these fractional exponents inside of it, talking about the accuracy of the different algorithms for PageRank. So that's the overall motivation for these sort of expressions right here. The actual problem here at this point is, though, just given an expression like this, how do we simplify that expression? And again, the procedure for simplifying these expressions is that we have two terms in this case, and we're going to compare those two terms to see which term is big O of another term. So we want to know, we have a question, is 1 over n big O of 1 over n squared? And I'll put a question mark there because it's a question. I'm not stating that at this point. Or we also want to know the question is 1 over n squared, big O of 1 over n. And again, the idea of big O here is that you can treat it, or the way you should be thinking about it is that this is an upper bound, like a less than or equal to sign. Like we're asking, is the thing on the right-hand side always bigger than the left thing on the left-hand side as n gets big? And we only need to keep around the thing that is the biggest. In this case, let's change my colors now, and we'll appeal back to that definition. In the definition, we have a limit. We're doing a limit as n goes to infinity of the f divided by the g. I'll say that the 1 over n right now, we'll use that as my f, and the 1 over n squared as my g. So over here, 1 over n divided by 1 over n squared. And if I simplify that, this 1 over n squared goes on top, n's cancel out, and we get that that part is equal to n. And we're taking the limit as n goes to infinity of the number n right here. So we get that this whole expression is going to be equal to infinity. I'm a little bit informal here with some of my notation here with this equal sign, that I'm trying to say that I'll use a barely visible color here, that like this internal expression right here, 1 over n divided by 1 over n squared is equal to n without the limit over there. And then this infinity over here is including the limit. So it's a little bit informal. In general, in this class, notation is not going to be something that I will care about. You can use whatever notations are convenient to you, easy for you to use, things that you've seen in the past. The important thing is just that you're going to be able to work through whatever the problem is and get the right answer. And again, most of the evaluation in this course done in one-on-one situations, oral exam. And so if there is confusion about the notation, you're not going to lose points. We'll just get that clarified, talk through it so that I understand what you mean, and then we'll keep going. And as long as you understand what you're doing, that is good enough for this course. But so now we have the limit as n goes to infinity of this f over g is equal to infinity. Going back up to my definitions up here, then we can say, okay, if something was less than infinity, then we have big O. And if it's greater than 0, then it is big omega. Well, infinity is not less than infinity, so it is not big O. But infinity is greater than 0, so it is big omega. And coming down here, it is not, in fact, big O. It's going to be big omega. So with my, we'll go that's white, that's not good, purple-ish color. We now know that this is 1 over n is in fact not big O of 1 over n squared. It is omega of 1 over n squared. A useful potential fact about big notation is that if the thing on the left is omega of the thing on the right, then the thing on the right is O of the thing on the left. And so without working through any more math, I do know that this is in fact 1 over n squared is equal to O of 1 over n. That 1 over n squared is like less than or equal to 1 over n. And if we just sort of plug in numbers in our head, like it makes sense that if we plug in a 10 over here for n, 10 squared, 1 over 100, that is a lot less than 1 over n. Plug in 100, 1 over 10,000 is a lot less than 1 over 100. So this direction here intuitively sort of makes sense. After I've identified that this term over here is big O of the term on the right, that means that it is not needed in the expression at all, that I don't need this 1 over n squared, and I can simplify this to just O of 1 over n like that. I did a lot of things right there, went really fast, talked really fast. I do that a lot, but I'll stop now for questions if anybody has questions about any of that. Yes?
Could you repeat just like the general steps so we can get through this problem?
Yeah, good question. The question is, repeat the general steps of what you did to solve these simplification problems. And the answer is that first you pick 2 terms. In this case, there's only 2 terms in the expression, so it's easy to pick 2 terms. And then you decide, is one of those terms big O of the other term? That involves a little bit of calculation, but we eventually decided that 1 over n squared is big O of 1 over n. Once you've identified that one of the terms is big O of another term, you can eliminate that term from the expression. So you pick 2 terms, see if one is big O over the other. If it is, eliminate it from the expression. Good question. Maybe a sort of aside meta thing too is that in this set of notes, so this is one of the more detailed set of notes that I have because there is no like reference text for us. And I've scoured the internet, scoured math textbooks looking for a good reference on simplifying big O notation. And as far as I can tell, none exists. That there are the very basic explanations, and then after that, everybody just assumes that you know how to do all of this more advanced manipulation. This is one of the, I don't know, in some sense, harder parts of the course because there is less reference things. But I think once you get the intuition behind it, it'll be relatively straightforward. I saw a hand up here somewhere. Yes.
Is there an answer for all?
Good question. The question is there an answer key for these packets? And the answer is that there is unfortunately no answer key for these packets. The reason for that is because I've tried in the past maintaining an answer key for things like this, and the answer key just ends up getting out of date, and so becomes less useful than not having one because you think you're wrong on an answer because I wrote the wrong thing there. So there is no answer key. That is the reason. But if for whatever reason, as you're working on these problems, you want to double check with me that like, am I right on this or wrong on this? Is this the right reasoning? Happy to look at that with you one-on-one, either after class, before class, or during office hours. I guess another announcement that I forgot to make is that I still unfortunately don't have the office hours posted. Hopefully by the end of today, I'll have it posted, but definitely by the end of the week, I'll have office hours posted. For certain special sort of notes packets, like exam prep packets, those will have answer keys associated with them. Good question. Other questions? Yes.
Kind of unrelated, but you mentioned earlier that you saw Monday this week of class.
Oh, thank you for bringing that up. We don't have class Monday because of Labor Day. Then we will not have a quiz on Wednesday. We will have it sometime later than that. Thank you. All great questions. Anything else so far? Okay. So let's move on to some new stuff here. And this next section here, section 3, called BLAS, so what BLAS stands for is the Basic Linear Algebra Subprogram. And this is a set of linear algebra primitives that many different libraries implement. And there's a lot of notes here, a lot of written material here. In general, in class, when the notes have written material like this, I'm going to not talk about the written material very much and expect you to read this on your own. If there are some things that are like particularly important, I might call attention to those. But the intention of this written material is for you to read on your own to understand what's here. So we're going to, in this section, be talking about the runtime of various matrix operations, various linear algebra operations. And in order to do that, we're going to have to talk about two different types of matrices, these dense versus these sparse matrices. And in mathematics, a sparse matrix is any matrix that has many zeros inside of it. We will be using this expression here, this function right here, NNZ, which stands for the number of non-zeros, the NNZ of a matrix, to talk about how sparse a matrix is. And this is a pretty straightforward, I think, concept that once it clicks, it'll be very straightforward for you. And so here I have 3 examples of matrices, and we want to count the number of non-zeros in that matrix. So this matrix A right here, I would call this a very sparse matrix because there are many zeros inside of it. And there are only 2 values that are non-zero. So the number of non-zeros of A is equal to 2. Whereas B right here, I guess I'll go ahead and write the word sparse right here because this is a sparse matrix, many zeros. B right here is a dense matrix because there are no 0 values. And here, the number of non-zeros, 1, 2, 3, 4, 5, 6, there are 6 non-zero values right here. Last down here, this C matrix right here, I've happened to have written to 0 as 0.0 in this matrix, but it's still just equal to 0 mathematically. And so the number of non-zeros right here would be equal to 1. A sort of subtle point about sparse versus dense matrices is there's no like hard cutoff about when a matrix becomes suddenly sparse versus dense. And yes, go ahead. Have I made a mistake? Yes, thank you. So I wrote the word one. I wrote the number 1 right here because there is 1 0 value, but we should have the number 5 right here instead of 1 because it is the number of non-zero values, not the number of 0 values. For whatever reason, people only ever talk about the number of non-zero values. Nobody ever, like there is no NZ for the number of 0 values. It's always the number of non-zero values, but it's an easy thing just to mix up in your counting of things. Is that the other? Yes. Yes, so this is our first typo up here that for typically most matrices that we would identify as being very sparse matrices have less than 1% of non-zero values right here rather than 0 values, less than 1% of non-zero values. So like most values are 0, and by most, I mean not like 50%-ish, I mean but like a lot. When we talk about the PageRank algorithm, we're going to see it's for the certain graphs that we'll be looking at, it'll be like 99.99999% of values will be 0. Yes. And so then the question is like, yeah, do we call A sparse or not? And so this goes back to like the percentage, like there is no hard cutoff on sparse versus non-sparse. Most people would call this a sparse matrix, but some people might not call this a sparse matrix. So yeah, no like hard definition between the two in the mathematical sense. It's just like a feel about things that we tend to think about sparse matrices different than dense matrices, And so by calling something sparse or calling something dense, we're not making a concrete statement about the matrix. We're making a statement about the way that you should be feeling about the matrix. Good questions. Any other questions so far? Okay. The confusing thing is that computer scientists came along and decided that these terms sparse and dense were great descriptive terms, and we made a bunch of data structures for sparse and dense specific matrices. But these data structures, are not specific to the mathematic sparse and dense matrices. A computer science sparse matrix can hold a mathematical dense matrix and vice versa. And we just use the same words for both, and you just have to know based on context, are people talking about the computer science version of sparse and dense, or are they talking about the mathematical version of sparse and dense? So the dense matrix, we'll go over, what we'll do next is talk about these actual formats of sparse and dense matrices from a data structures perspective. And dense matrices, I think, are intuitive. They make a lot of sense. They're probably, if you've been exposed to matrices and programming at all, it's probably the thing that you've been exposed to. And the dense format is just you store every number in a block of memory. And there are a lot of subtleties that go into how to do that efficiently. We're not going to care about any of those subtleties in this class. Again, you are not going to be implementing a library for dense matrices versus sparse matrices. We will only ever be using other people's libraries. And so we don't need to know about any of those subtleties. We're just going to need to know about some of these high level details. And so this is enough information for us for the high level detail. The sparse matrix, though, is a little bit more complicated. And for sparse matrices, there are many, many different formats possible. Many data structures available. The simplest one of those formats is what we'll go over today. It's called COO. And this is the format that is also used in PyTorch, And your first programming assignment that we'll be using PageRank in a couple of weeks will be based on needing to understand this COO format. So we're going to go over it at a very high level right now. But then when we get to the actual assignment, you'll see how this more literally translates into code. In this format, what we do is for each non-zero value, store the coordinate of that value. So the COO up here in the name of this storage format comes from the fact that we are directly storing the coordinate. And then we also store the value. The advantage of this format right here is that if there are many zero values, they will not be stored explicitly in the COO format. They will not be stored explicitly, and that will imply both memory and runtime improvements. In the next parts of this notes, I'm just going to state what those improvements are without any like descriptions of the algorithms that results in those improvements. So you don't need to necessarily know why you're getting these runtime improvements. You're just going to need to know what they are. But hopefully it should make some sort of sense that if you have a lot of zeros and you're not storing them, then you can do things faster and use less memory. Yes, question? And both no coordinate and no value. So the explicitly right here, the question is, why did I say the word explicitly? Is we can say they're like implicitly stored by the fact that they don't have a coordinate and value pair. If there is a, whatever coordinates are not in this list of coordinates right here are implicitly 0. Yeah, does that answer the question? Yes. Yeah, the question is, do we need to know how the set of coordinates and values are like physically stored in memory or how to access them in Python? Eventually, you will need to be able to do some stuff in Python with this, but at this point, that's all sort of like implementation detail. At this point, the only thing that's important is that for a computer science sparse matrix, which is the actual data structure, it means that we're just not storing anything that's 0. You don't need to know anything more detailed than that. Good questions. There are many other of these sparse formats that have even more reduced memory usage or better computational properties. But this COO is the simplest, and everything that these notes state are also true of every other possible sparse format. So really, whatever sparse format you're using doesn't matter so much. It's just the fact that you're using something sparse instead of something dense means that you get these improvements. Okay, so now let's talk about exactly what those improvements are. And the first, which we sort of talked about here, is memory usage. And hopefully it's roughly obvious that the memory usage of a sparse matrix is going to be the number of non-zeros in that matrix, because you have to store the coordinate and the value for each one of those non-zeros, but you don't store anything for any 0 value. So we get theta of n of a for the memory usage of a sparse matrix. If you have a dense matrix, though, then the memory usage is going to be theta of m times n. This problem 6 right here, I'm not going to do it in class. This is the sort of problem that would be a good oral midterm sort of problem. But this is really just a test of your understanding of the theta O omega notation. And it happens to talk about like sparse and dense matrices and their storage requirements. But it's more of a test of your understanding of the big O asymptotic notation than it is about the matrices themselves. So there'll be a handful of problems like this that I will skip over, just highlighting that these will be something that you'll want to prepare for before the midterm exam. It's the memory usage stuff. This note 5 right here is saying that you will be expected to be able to perform basic calculations about the exact amount of memory for dense matrices, but not necessarily for sparse matrices. And so problem 7 and 8 are just asking you to do those basic calculations. So we'll just do problem 8 right here. So you have a data set with 2 to the 10 columns, 2 to the 20 rows. So the total number of numbers here is 2 to the 10 times 2 to the 20. The number of rows times the number of columns. And that is equal to 2 to the 30. We're storing here in 16-bit floating point numbers. So this, we have 10 to the 30 numbers. And then we have 2 bytes per number. 16 bits equals 2 bytes. That equals 2 bytes. And then so 2 bytes per number. And so that's a total of 2 to the 31 bytes that we are storing here. and some simple, straightforward math that you should probably know is that 2 to the 10 is equal to 1024, or about 1,000, about equal to 1,000. And so this is about equal to 2, 1, 2, 3, 1, 2, 3, 1, 2, 3 bytes, which is 2 gigabytes. So you need 2 gigabytes to store this amount of data. This is the sort of calculation that a practicing data scientist really needs to be able to do in their head, just looking at a data set, quickly getting a sense of how much data is this going to take. So can I load it directly into memory, or do I have to do something fancier in order to load it into memory? Any questions about this problem or this type of problem?
Would it actually be 6 gigabytes then?
Question is, would it actually be 6 gigabytes?
For the answer?
So the answer here should be just 2 gigabytes.
Oh, okay.
Yes. Sorry, I can't hear you. So the question is, how did I go from here down to do all this mental math-ish? What I'm about to say, not important at all for the class, but it is very important for you in life, because this is something that if I were interviewing somebody and they couldn't do this off the top of their head, it would be a clear indication to me that they have not dealt with bytes very much. But so if we have 2 to the 31, that is equal to 2 times 2 to the 10 to the third, and 2 to the 10 is about equal to 1,000. So that's equal to 2 times 1,000 cubed. And so each one of these 3 groups of zeros right here corresponds to these 1,000s, and this 2 out here corresponds to this 2. Again, for the purposes of this class, like, these tricks, not important. You'll have on quizzes, like open note quizzes, you can just type this into Wolfram Alpha and get whatever the number is. On the exams, the oral exams, which you will not have access to a computer to do that. You'll have to do things on your own. They're going to be much more like concept oriented, like this problem that we skipped up here, problem 6, concept oriented rather than calculation oriented that we did right here. So
From the final answer, is there a way we can say how much storage would it take for bit floating point? From the 2 gigabyte balance? The final answer is 2 gigabytes, right?
Correct.
Say we're using 4-bit floating point to store the value. Can you convert that to
so the question is here, if we were using a different size, say 4-bit instead of 16-bit, well, 4-bit is 4 times smaller than 16, so we would just divide this by 4.
So we can do it from the final answer.
I can do it from the final answer. Yeah, the mechanics of doing something like this, the calculations, not how you, lots of different ways to go about and get that. And I think they're the less interesting thing. I want to, if there are more questions on this topic, happy to answer them later, but this is like the least important thing in this notes packet, so I want to move on. And so I'll get those questions later. Sorry about that. Okay, more important things. Usually we're going to be talking in this class about so again, like at the very top of this packet, the purpose of this packet is we're going to see a lot of linear algebra expressions, sort of like this, and we want to be able to understand which of these linear algebra expressions might be faster or slower to compute. And in order to do that, we're going to actually write out the asymptotic runtime of computing something like this. And so now in this BLAS section, the main focus of this is building up the machinery in order to do that. And this BLAS set of subroutines, this library, is divided up into 3 levels. level 1, 2, and 3, starting with the most simple things going to the most complicated. And so those notes are organized that same way, going from the most simple to the most complicated. In the level 1 operations right here, these are all vector-only operations with no matrices. Anything that is a vector-only operation is going to be a BLAS level 1 operation. And it turns out that the runtime of any of those operations on dense vectors is going to be theta of n, where n is the size of the vector. And if it is sparse, then it will be, if there's only one term, n and z of that one variable. But if there's two, it'll be the sum of the total number of non-zero terms in the expression. So we'll do a bunch of examples here. I think the examples will make that a little bit more clear. But so let's say we have, so x here is a vector, 5 is a scalar. We're doing a scalar multiplication. If we were to have a dense scalar multiplication, then the runtime of this would be theta of n, and the runtime of the sparse would be theta of n and z of x, like that. In general, for any of these expressions, I'm not going to give you like the explicit dimensions that I want you to use for any of these variables. So you'll have to somehow identify that, okay, x here, we're going to identify x as being a vector in r to the n. And so we'll make our statements down here based on n. But you could use r to the d or r to the m or whatever set of letters that you want for any of these equations. That is the choice of your name of variables is not an important part of this process. The important thing is just that you identify that it is linear or linear in the number of non-zeros. Any questions about this problem 9.1 here? Okay. Thinking about like quizzes, exams, things like that. These problems here are all too basic to show up on a quiz or an exam. These are just like practice to getting so that we have these set of tools so that we can do the more complicated problems that are likely to show up. Okay, so that's part 1. Part 2 over here, we still have a scalar multiplication here of 0 times x. And there is some sense where like I know this answer instantly. It doesn't matter what the dimension of x is. I know if you multiply anything times 0, you get 0. And so you could think there is a way possibly to do this in constant time. But anytime you're explicitly asking the computer to do this multiplication here, it is going to go through and do all of those multiplications by 0. And so this will have the same runtime as above. Don't ever try to like think about simplifying your expressions in order to cut down the runtime. The fact that this is a 0 right here and you could simplify this doesn't matter for our purposes. Yes?
So what is the number actually?
What is what number actually?
Like 5 versus 0.
So if x was equal to 1, 2, 5x would be 5, 10, and 0x would be 0, 0. So just like the scalar multiplication of the number over here times the vector. From a runtime perspective, it doesn't matter what that number is. Yeah, any number is the same as any other number. Transpose of two, or the dot product of two vectors here, x transpose y. This is the dot product of these two vectors, the dot product. And this again has the, if these are both dense, then the runtime will be theta of n. Again, I'm not going to write, well, I guess I will write it out, that the x and the y are both dimension in like this. And then for the sparse case, it's the total number of non-zero entries. So theta of nn z of x plus nn z of y like that. If you were, so this is not a required thing to do, but if you were to think about like how these numbers are actually stored and how you are computing any of these values, these runtimes here would be like the obvious runtimes of, if you just do the obvious thing to do these calculations, you'll get these runtimes. And then the vector norm down here, even if you don't know exactly what this is called, the L1 norm right here, you don't have to know what that means in order to calculate the runtime of this, because like we said, for every BLAS level 1 operation, everything that is only involving vectors, the runtime is going to be for the dense, theta of n, and for the sparse, theta of n and z of n. Yes.
Is there any reason you would try to calculate it from as
So the question is, what would happen if one was dense and one was sparse? And it turns out in that case, either one of these two formulas would work, and they would both be equivalent to each other. So if you have two vectors and you're doing a vector operation with them, then either one of these formulas ends up working. The reason the sparse formula down here reduces to the dense formula is that if you have a dense vector, say x right here is dense, then the number of non-zeros of x is equal to n, so you have theta of n, which is theta of n. So that is something that could conceivably happen, but the things to remember are just the dense and the sparse only cases. Good question. Back first and then front, yes. Yes, what is your name?
I'm
Kate, okay.
For problem 4, I was wondering why for the sparse matrix it's theta of n z of n and not n z.
Okay, that should be an x right here. Anytime you have the n and z, it should be the actual name of the vector. Anytime you have a, without the n and z, just inside the asymptotic notation directly, it should be the dimensions of the vector. Yes, so that's a good catch. It should be the n and z of x here, not the n and z of n. Thank you. Ambika. Everybody just says n and z. That n and z stands for number of non-zeros. The double bars with the one right here, this is the L1 norm of the vector. We'll be using this L1 norm of x. This will be something that we will use a handful of times throughout the course. And that's a good segue into the next problem right down here, where it's asking you the formula for 3 of these different norms. It's called the L1 norm right here, the L2 norm, and the L infinity norm. This is something that, I will not write out the answers right here. I am going to force you to look them up or figure them out on your own somehow. Just asking ChatGPT is, I'm sure it'll give you the right answers for something like this. But we'll be using all these different norms throughout the class. Again, all of this is things that I think should be review from the linear algebra classes, but if it's not 100% review, the reasons that I am giving some things as problems that we're not doing in class is to force you to find some sort of reference that is going to be helpful for you to find review in order to understand what these things are. So good question. Any other questions so far? Okay. BLAS level 2 is for vector and matrix operations. We will not talk about these explicitly. So a vector matrix would look something like AX or X times A. We will not talk about these explicitly because they are totally subsumed by this BLAS level 3 operations, which is matrix times matrix. So something like we have a matrix A and a matrix B, multiplying those two things together. And you can get whatever the runtime, appropriate runtime is for the level 2 things just by considering one of these matrices to be a vector. There is a lot of little notes inside of here, inside of this BLAS level 3 section. And inside of these notes, there's a lot of various formulas here. So like the runtime of matrix multiplication here, if we have two matrices, m by n and n by o, their overall runtime is m n o. This is something that absolutely everybody will need to have fully memorized by next week. There are other things, though, that are slightly less important that won't come up in any of the practice problems, but they're stated in here because I think they're interesting. And things like this number right here and these right here. These are things that if your goal is to get an A in the class, these are the sorts of things that you will also need to have memorized and be able to talk about them a little bit with me. So what overall big picture is this talking about? So this is talking about the runtimes of matrix multiplication. And there's a very famous problem, the runtime of matrix multiplication, because we actually do not know what the optimal runtime of matrix multiplication is right now. And very famously, we don't know that. I'm going to visit this link for us down here really quick on Wikipedia, the computational complexity of matrix multiplication. Big thing down here, and we're going to jump down to this matrix multiplication exponent to see this little table right here. That since the beginning of time, since people first discovered linear algebra, everybody knew that the runtime would be at worst cubic. And people were very astounded in 1969 when Strassen here invented a new algorithm that was O of n to the 2.8074. Better than cubic. Nobody thought it was possible until he showed it possible. And then repeatedly, people have getting these exponents down even farther and farther. And you'll notice that here between like 2014 or 2012 actually and 2024, these like improvements in exponents are way, way out over here to the right decimal over here. And actually just this year was a huge breakthrough in mathematics. So Williams, Shu, and Zhu went from 2.371866 down to 2.371552 in the exponent of matrix multiplication. And lots of comics at the time going around about how these like exponents got down to some very, very basically the same number, but mathematicians around the world amazed, computer scientists around the world amazed. In this class, again, we're not going to cover any of the details of these algorithms. You don't need to, for any of the problems we're going to work on in class, you don't need to know the details of those numbers. But the notes here include all of the highlights of the things that I think an educated data scientist or an educated computer scientist really should know about this, so that if you're talking with people in interviews or at conferences or something and this comes up, you are, you know at least roughly what they're talking about. Again, the things that you absolutely have to know, though, are this AB takes time O of m times n times O in the dense case. And then down here in the sparse case, we'll get n and z of A. So if we have A times B, the number of non-zero elements in the first matrix times the outer dimension of the second matrix. This B right here, this O is the outer dimension of that second matrix, and that's the runtime in the sparse case. Those are the things that you absolutely have to know just to pass the course. Everything else in this section is if you want to get the A in this course. Any questions? Blue is need to know. Everything else is good to know. Yes. Yes. So is Arsh, is that right?
Yes. Yeah. Other classes, because they said background noise class or
Good question here. So in PyTorch, so yeah, one of the things we'll get to in a little bit, PyTorch does not allow multiplying two sparse matrices. And that's a very common thing in linear algebra libraries, not being able to multiply two sparse matrices, but only being able to multiply a sparse times a dense. So this is, in particular, the runtime of a sparse times a dense matrix, where B is dense and A is sparse. When we get, we'll do the example problems down here, actually computing some of those runtimes, and that'll make it maybe click a little bit more about those situations. There's a problem that explains that reason. Yes, good question. Yeah. Do you all have a question, Dan? Question is, what do these levels mean? The answer is that if you're using a high-level library like PyTorch, the BLAS levels are going to be hidden from you, but you will still see people talking about these BLAS levels. There are lower-level libraries that say only implement BLAS level 1 and 2 operations and don't implement BLAS level 3 operations. The levels thing here, you don't need to know at all what the what levels correspond to. So you don't need to know exactly what's the difference between the different BLAS level 2 and BLAS level 1. Don't need to know the levels. I've just organized the notes this way because you will hear people talking about BLAS levels, and so it's useful to have heard that term once at least before. But the BLAS level 1 was vector-vector, BLAS level 2, vector-matrix, BLAS level 3, matrix-matrix operations. Okay. Any other questions so far? All good questions. And a lot of maybe, I don't know, this first set of notes, especially a lot of just dry, repetitive, here's a bunch of facts shotgunned at you one after the other. That's because we just need this background information in order to be able to talk about these algorithms. Once we get into the subsequent note packets, things will get hopefully a little bit more spicy and interesting about what's going on, less just shotgun of facts. But we have to get through these facts in order to be able to do the interesting stuff. So here, problem 11, we have a bunch of different operations, and we'll just walk through what are the runtimes of these operations. Again, here I have this note, you should report the answer for every possible combination of sparse and dense matrices. And this note up here says that you'll have to specify, anytime there's a formula, you will have to specify what the dimensions of these various matrices or vectors are. And you'll have to make sure that they match to make sure that the formula is well-defined somehow. So here we have A plus B adding two matrices together. That's only well-defined. It only makes sense to do if A and B have the same shape, the same number of rows and columns. So I will say both A and B have the shape of R to the n times m. Sometimes, since everything we're going to do in this class is the real numbers, I'll very often just say like n times m and leave out the r here for the real numbers and just write the dimensions over here. Okay. If we have, let's keep it thread. If we have two matrices where we are doing essentially a vector operation on those matrices, so here addition of two matrices is the same as addition of two vectors that are just shaped kind of funny, the runtime is going to be exactly the same as those two vectors. Again, the notes up above have that explained in a little bit more formality, but here the runtime in the dense case is going to be if we treat these as vectors, they have size n times m. So the overall runtime is theta of n m. And if this is the sparse case, then the overall runtime is the number of non-zeros in n z of a plus the n z of b, like that. Any questions about 11.1? Okay, 11.2 here, the only difference between 11.1 and 11.2 is this transpose. And transposes in every linear algebra library, transpose always takes constant time. Transpose takes time theta of 1. And essentially what the libraries do, they just have a flag that they store whether the data has been transposed or not transposed. They don't actually go through and rewrite the data in memory. So transposing always takes time theta of 1. And so the runtimes here are going to be exactly the same as the runtimes up above. Any questions about transposing?
So will it be, the extent would be theta n plus theta 1?
So the question is, so here, we'll just write it out here. So in the dense case now, we have A plus B transpose, and doing the transpose, performing that transpose takes constant time, and then the addition takes time n times m. So it's just theta of n times m plus 1, which simplifies to the theta of n times m. One further, at this point, if you were to stop and be done, that's totally okay. But you can also observe that because there is a transpose right here, B transpose would have to be the shape of n times m, which would imply that B itself has shape m times n here. You wouldn't have to write out like this, I don't know, details about thing. That's a thing that you should be aware of with these transposes and how they're changing the shape. But still theta of n times n. That we add this one, the way the runtime works out is you add the two runtimes together of the two operations, and the one here simplifies out. Does that answer your question? Okay, here in problem number 3 right here, we have a scalar multiplication. Scalar multiplication on a matrix is the same as scalar multiplication on a vector. So again, it'll be the dense is theta of m times n. Same shapes of the matrices, so I'm not going to rewrite that. And then the sparse is going to be theta of n z of a, like that. The first interesting one here, which is actually involving two matrices doing interesting things to each other that cannot happen with vectors, is problem 4 right here, where we have the matrix multiplication. And here we will be a little bit more careful with our asymptotic notation. Everything that I've done so far has been with the theta, but here with A and B, I'll go ahead and write out A has m by n and B has n by O. It is going to be important that our runtime now for the dense operations is going to be big O and not big theta of m times n times O. So big O and not big theta here. I'm going to scroll up just for a second to remind us why. In this big long explanation of different things about matrix multiplication, up here, the blue thing, the thing that you absolutely have to know is that the runtime of A times B is O of m n O. And again, we don't know what the optimal runtime is, but we know that it is smaller than this. We have, for example, algorithms that compute it in n to the 2.3171552. But we don't know what the optimal algorithm is, and so we cannot put a theta here, even if we wanted to. In general, even when people are talking, even when we're using these more optimal algorithms, these faster than cubic algorithms, people always write the runtimes when they're thinking about linear algebra formulas with these cubic runtimes. In practice, most libraries implement the cubic runtimes and not the faster runtimes. So in practice, most libraries actually use cubic runtimes. I'm calling this cubic because there's 3 things that are being multiplied together. In practice, most libraries use cubic runtimes, and but we can't be theta. Still can't say big theta instead of big O. We also have to think about the sparse. Sparse. So again, this is the thing that you absolutely have to know for this class. The runtime of A times B when A is sparse is the number of non-zeros in A times O, the outer dimension of the rightmost matrix. So sparse here will be O of n Z of A times little o right here. This is the big O from the asymptotic notation on the left, and this O right here is the little o, which is the same as this O right here. Those 2 things are the same. Any questions about 4 there? Yes.
I have 2.
Sure.
First, in notes, it says sparse data.
Yes. Okay, good question. So up here, I have theta NNZ A times O, and down below, I wrote big O. What I wrote down here is correct because theta implies O, so this is a correct statement right here, but it is also correct and more correct, a stronger statement to make to put the theta right there. Yeah.
And relate that one towards why the density data as.
So the question is on problem 11 here with the 1, 2, and 3, these additions and the scalar multiplication here. Why is the dense theta of n times m? There's many levels of the explanation to this. The sort of most detailed level would be us actually having to write out some pseudocode of what these algorithms are doing. And we're not going to go through and do that. The highest level, the thing that is acceptable for this class, that is a good thing to do, or a sufficient, that you can get an A in this class if this is where you're at, is just to memorize this fact that the addition of matrices is, in the dense case, theta of n times m. Somewhere in between, which is potentially useful for you, but if it is not useful for you, then you can totally discard it, is that you can think of a matrix that is of shape m times n. You can think of these matrices as vectors. These are, we'll just do B is like a vector that's in R to the mn without the little x right here. So it's not a matrix where one is rows and one's columns, but it's the total number of rows in this vector is m times n because this is the number of entries in this matrix right here. And if you were to think of this as a vector instead of as a matrix and appeal back to the BLAS level 1 operations, then you would get these exact runtimes here. So if that like intermediate explanation is useful to you, then that's good. It makes it easier to remember the runtimes for matrices. If it is not useful for you, then you can totally forget about it and just straight up memorize these results for matrices. So yeah, unfortunately, I in general hate forcing students to memorize things, but there are a lot of memorization stuff that I just have to do about runtimes in order to get to the interesting stuff of analyzing algorithms. Did that answer your question? Cool. Great questions. Any other questions at this point? Yes.
Can you explain why it's
Which problem?
like what's the intuition behind getting
Good question. Question here is on 4 for the sparse entry right here. What is the intuition behind this? The answer is that a proper explanation of that would be like a full semester's long course of diving into the formats of sparse matrices, which we're not going to do. Something that is maybe useful to you though, and this is another good way to be thinking about algorithms, is that we have this n and z of a right here. And let's think of like, what are the possible ranges of n and z of a? Well, the most that n and z of a could ever possibly be equal to, the upper bound of it, the smallest upper bound of n and z of a would be m times n. That a over here can have at most m times n elements inside of it. So the total number of non-zero elements in A can be at most m times n. And if we were to plug this into the formula right here, when the matrix A here has m times n elements, it is the least sparse possible because it has no zero elements. So it is the most dense matrix possible. And if we were to plug in the most dense matrix possible here into A, then we would get the dense matrix formula. We kind of reduce to that. In the case that we have more sparsity than that, then you can see that this will, in fact, number here be smaller than this number up here. And so we can get some speed up from that sparsity. Again, I think that's something, an intuition that might possibly help you memorize some of these formulas. But if that's something that's not helpful to you, then that's okay to just throw it out and memorize that sparse is n and z of a times O and dense is m and O. Good question. Any other questions right now? Okay, next time in class, we will start putting these together into actual interesting expressions. This is a good stopping point for us for today. If anybody does have more questions about anything, happy to stick around and get those answered for you. Otherwise, I hope you all have good weekends. There's no homework over the weekend, but I suggest reviewing these notes, making sure that you understand them as much as possible for Wednesday of next week. Let me stop this.